The linear expansion of metals is primarily caused by an increase in temperature. When metals are heated, the atoms and ions that make up the metal lattice gain kinetic energy, leading to an increased vibrational motion. This increased vibrational motion causes the individual particles to move more wildly around their average positions, which results in the overall expansion of the material. Welcome to another video, guys. Here we're going to be talking about one-dimensional expansivity, which is basically the linear type. We'll actually have three different dimensions at which this expansion occurs. You've got the linear dimension, you've got the area dimension, and then you have the cubic dimension. We'll make videos on those other ones later on, but then here let's start off with linear expansivity. The expansion coefficient is a measure of how much material expands per unit increase in temperature, and it varies from one metal to another. It's actually a constant. And each metal has its own number, as you will see in the examples that we'll touch on in this particular video. The equation you have on the screen, that's linear expansivity, equals increase in length, that's L2 minus L1 over original length, and that's L1 times temperature rise, which is theta 2 minus theta 1. And that is what you have as delta theta right here. Linear expansivity is measured in per Kelvin, length measured in meters, and then you've got temperature measured in Kelvin or Celsius, depending on what kind of example you're working with. Alright, let's deal with this particular example. A brass rod is 2 meters long at a certain temperature. What is the length for a temperature rise of 100 Kelvin if the expansivity of brass is 18 times 10 raised to the power of minus 6 Kelvin? You have this equation on the screen. The equation we looked at earlier. You actually need to be able to recall this equation. Linear expansivity equals change in length over original length, that's L1 times temperature rise. You have the original length from the question, that's 2 meters. You have that right here in place of L1. You have the change in temperature taking the place of delta theta. You have that right here. You have the linear expansivity given to you as 18 times 10 raised to the power of minus 6. You have that right here, taking the place of this in that equation. And what else? Yeah, that's about it. And then you have these two repeated. Now, when you solve arithmetically, you end up with L2, which is 2.0036 meters. That's that for that question. We'll have a second question here. It says the linear expansivity of a metal P is twice that of another metal Q. When these materials are heated through the same temperature, note that, through the same temperature, their increase in length is the same. Calculate the ratio of the original length of P to that of Q. Now, one thing we note here, every other thing is different apart from the temperature and the original length. Not exactly. One thing we should note here, you have the same temperature for both metals, and then the increase, change in L, change in length for both of them is the same. So we're not going to focus on that. But let's start off with this comparison. Linear expansivity of Q is alpha, and then linear expansivity of P, you've been told from the question, is twice that of another metal. That's just 2 times the linear expansivity of Q. Right? We have this equation representing the general equation, right? Now we're going to fine tune this equation for Q, and then we'll fine tune this equation for metal P. So fine tuning it for metal Q, we've replaced this original length with LQ. Right. We're not touching this because the question says the increase in length is the same for both metals, so that's why we're not touching this. We're not touching these as well. This is the only guy changing, and probably this when we get to the next one. Fine-tuning for metal P, I think I should add that here for metal P. All right, we have that right here. Since the question says metal P, the linear expansivity is twice. All right, you have that right there. Like I said, we're not touching this. We're not touching the change in temperature. They're kind of the same. LP, which is the original length, we've changed that from L subscript 1 to L subscript P. All right, so we have equation 2 and equation 3 right there. And then the next thing we're supposed to do, since the question says we should find out the ratio, so we're pitting what we've got for equation 2 and what we've got for equation 3 against each other. But firstly, all right, we need to make the original length for both equations the subject. All right, and that's what we've done for equation 2. So we're bringing this right here. We're making the original length, which is L subscript Q for metal Q. You make it the subject of the equation. You have that right here. And then you have for LP, making it the subject of the equation, original length for metal P, and that's what we have here. This equation, you have it right here, where you make L subscript P the subject of the equation. That's the original length for metal P. And now we have what we can pit against each other. We have the equation for the original length for metal Q, then equation for the original length of metal P. So we've interpreted that particular question. So we have the ratios. Original length of metal Q, you have that right here. You have for metal P, you have that right here. So let's do our, so we have this cancelling this. We have this cancelling this. What else? We've got this. So we're left with 1/2 here. All right, 1/2, and then this whole thing for what you have on the right is 1. So you're left with half ratio 2. So the ratio of metal P, the original length of metal Q, is half to original length of metal P is 1. And we can just do something right here, just to get rid of the fractions. For us to have all whole numbers multiplied by 2, you'd have 1/2, which is our final answer. So ratio of original length of P to that of Q is 1/2. That's where we would stop for this particular video. If you got questions, you can drop it in the comment section. So I'll see you guys in the next video.